Okay, so welcome everyone to Paper Club. Today, Amin is going to be speaking about using mutual information for learning in language tasks, which is actually an interesting approach because natural language processing is usually based on negative log likelihood. So this should be an interesting discussion about how concepts in other areas of machine learning can be translated to natural language processing. So go for it.
Yeah, thank you, Carlos. Let me just share my screen. Okay, can everyone see that fine? All right, brilliant. So yeah, today's paper is a mutual information maximization perspective on on language representation learning. So yeah, as Carlos said, I found this paper quite interesting, and I hope the attendees here today do as well. So the paper has two goals, I think. The first is to unify the word representation learning methods that we've seen in the past. So namely Skipgram, the BERT model, and ExcelNet. And it shows that they are all instances of maximizing the mutual information between different views of a sentence. So we'll get into what different views of a sentence, what the different views can be, and it's actually a lower bound on the mutual information which is maximized, but we'll get to that. And the second goal of the paper is to introduce a new self-supervised objective, which combines an aspect of BERT and an aspect of where this mutual information idea has been used to get representations of images, combines them, and then uses this objective to get representations of words. So, okay. I guess a couple points from the introduction before we move on. As we all know, the state of the art of NLP involves pre-training a large encoder on a massive corpus of text to get an encoder which can generate representations of words, and then this is then used downstream on various tasks, and there's great flexibility on how the representations can be used afterwards. Okay, so a big idea in the paper is that of contrastive learning. So the idea behind this is, what you want to do is you want to divide your data into different views. So in the example of a sentence, you might take a word and the words surrounding that word, and you want to maximize the mutual information between these representations, and you want to do that against other inputs known as negative samples, which are outside of the context. So we'll see how the Skipgram, also known as Word2Vec, BERT, and ExcelNet all fit under this this framework, and then we'll get to the objective that's proposed in this paper. So I guess we can start with, well, what is mutual information? So as a reminder, mutual information describes how much, so mutual information between two random variables describes how much C in one of them realized reduces the uncertainty in the other. So in this case, uncertainty is measured using entropy, Shannon's entropy, and so the equation here fits exactly that description. And so, as it says, the goal is to learn a function that takes the two views of a sentence here.
Sorry, I mean, we have a question about so about the different views of a sentence.
Yeah.
So if you can provide an example of what this means, having different views of a sentence.
Sure. So there are many examples of what that means in the paper. So I think it's probably best until we get to the models themselves. But an example is given a sentence, you have an encoder which gets a representation of one word, and you want to maximize the mutual information between that and some aggregated representation of the other words in the sentence. So that's an example. There are many examples we'll get to, but that's one of them. I hope that answers your question for now. Okay. So yeah, the goal is to learn a function which maximizes the mutual information between the views. The issue is that there isn't a way to formulate the mutual information when the function is something like a neural network or contains a neural network or contains a transformer encoder, for example. So what actually happens is you maximize, in practice, you want to maximize a lower bound on the mutual information. And this is given by this equation.
Can I ask a question? I'm a bit confused about this mutual information of different views. So you're saying each view could be an encoding of a subpart of your sentence.
Yeah.
And would mutual information then mean that if I know one part of this encoding, I could sort of predict what the other encodings would be?
Exactly, and that's what you train the model to do, to be predictive of its context, or given its context to be predictive of a view or a word of a sentence, and through that representations are learned. Okay,
thank you.
Yeah, so let's talk about briefly where this loss here comes from. So this is the info NCE loss. I think it would be good to jump to the paper. Oh, this is the wrong paper. Okay. So the main idea behind this loss is you're turning a problem involving a generative model into a classification problem. So in the example here, let's imagine that xt plus k is a word at a later part of the sentence, and the context here encodes some representation of the sentence before. Although in practice, it doesn't have to be autoregressive in this way. But the main idea is, instead of directly modeling this probability, you instead model a density ratio which preserves the mutual information between the two views. And so you instead use a cross-entropy loss to measure how well the model can classify a word amongst some negative samples. And so let's have a look here. So this loss here is the cross-entropy of correctly identifying a word amongst a bunch of negative samples. So in this case, negative sample means words that are in the corpus but aren't in the context. And as Arvid pointed out, you want the model to be predictive of words in the context, and to be able to differentiate between words in the context and outside. Okay, so
if I can add something. Oh, go ahead, Arvid.
Yeah, I was just wondering, because if you just say anything that is not within the context, you could, in principle, have the idea that the same context is repeated somewhere else in the document, right? So you sort of make the assumption that this doesn't happen often enough to be a problem for this predictive task, right?
Yeah, so that's actually what I was trying to get to, is that so or at least the if we think about Word2Vec, for example, which were some of the first successful models that used noise contrastive estimation, they make this assumption that most of the context is going to be noise. So when you're reading text, most of the things surrounding a word are not actually required to make the word into a vector. And yeah, so they use this idea that you can sample from the vocabulary with a certain distribution, and most of it will be noise. But let's call it in those moments where you sample things that are actually relevant, your predictive capability goes up, and that is backpropagated through the network, and that's what starts making embeddings make sense. That's a very high level view, but the idea behind NCE is that most of your context is noise, and you're trying to figure out which parts of the context are not noise by randomly putting words in the context.
Yeah, but when you say randomly putting it in, there's a chance that you actually put something in that could be considered helpful in that particular instance. It's just rare to happen, right?
Right. So I guess it also depends on what you consider the context. But as Carlos says, that if you're sampling from, for example, the unigram distribution of the entire corpus, you can assume that the noisy samples that you get won't be useful in the context on average. So yeah, as you say, you might have cases where that isn't the case, but in expectation, you'd expect it to be that way.
Gotcha. Thank you.
Okay, so where were we? All right, so this is where this loss here comes from. There's a point here about how this relates to the standard cross entropy. So in cases where your noisy set, which contains the word that you want and a bunch of negative samples. In the case where that includes the entire corpus, this just becomes a standard cross entropy loss, and there are some methods which don't use negative sampling, like for example BERT, and that comes at the cost of of computational efficiency, but you don't need to approximate in that case. So where does this lower bound come from in the first place? So if we go to the this paper here, let me just show the title because I didn't before: Representation with Learning with Contrastive Predictive Coding. They show that this loss, also seen in the paper we're discussing, so maximizing it maximizes a lower bound on the mutual information. So this is in the appendix of this paper. Please do jump in if you'd like to see the derivation. But this is the idea, and you can also see that the bound here becomes tighter as you increase the number of negative samples that you have by this term here. Okay. Okay, so I think going into the models would make things a bit clearer. So seeing some examples. So the first model that we'll discuss is the Skipgram model, and the central assumption behind this is that a good word representation is one that is predictive of its context. So I'm actually going to go to oh, it's not up here now. Okay, no worries. I was going to show a nice diagram of the Skipgram model, but we can just describe it. So the way that the training examples here are generated is by taking a sliding window across the corpus, or just looking at sentences as a whole, and you generate word context pairs. And so your training samples are a word and one of the words that appears in the context, and yeah, so for example, if our sliding window was size 5 on this text, then we might have the training examples word context pairs start with and start with first and start with we, and so what you do is so you have a model which sorry, I'm trying to get my thoughts together here. I think it would be good if we just show the example here. So let me go to this part. Okay. Did you want to say something, Carlos?
No, just that we discussed this paper in Paper Club a while ago. So if you go through a list, you can see this Mikolov reference.
Okay.
But but please go ahead.
Sure. Yeah. So you have an embedded matrix which is learned, and a context matrix which is also learned, and your training examples are context word context pairs, and the representation that you're interested in is this hidden vector in the middle. And so this is just a softmax over your vocabulary. In the case of when the vocabulary is large, this is just approximated using negative sampling. But yeah, that's the Skipgram model. So how does this relate to the framework? Well, if you see, so this is the objective function of the Skipgram model, and the probability of a context word given a word token, and we define the function that we're interested in, the one that's in the loss, as a dot product between the representation of the context and the representation of the word. And so in this case, g of phi would just be, where is it? G of phi would just be this mapping between the one hot encoded word and the row of the matrix, and the same for the context. So okay. So by simply defining g of phi and g of omega here as the embedding lookup functions, as we saw before, you can see how it fits into this framework. And yeah, so I guess another small point about how negative sampling is used. You sometimes also want to subsample your corpus. So instead of sampling from the whole corpus, you would remove with probability proportional to how frequent the word is in the corpus, and then sample from those words. And so this stops you from having many stop words in your negative samples. So you're not training a model which compares context words to just many different stop words. Okay, so that's the Skipgram model. Now, how does BERT fit into this framework? So we've discussed BERT before, and the way it works is it's trained on two tasks. So the first is masked language modeling, and the other is next sentence prediction. So they say that because there has been work done elsewhere that shows that if you train a BERT model on only one of the tasks, namely the masked language model, it still can give good representations. And so they leave showing why the next sentence prediction objective fits in the framework to the appendix. Oh, let's not go there now. Okay. So let's see how the masked language model objective fits in this framework. How it works, as we've discussed before, is given a sentence, you want to replace 15% of the tokens by either a mask symbol, a mask token, 80% of the time, another random word in your corpus 10% of the time, or just the original word. And the objective here is to train the model to predict the missing word, or the masked words given the other words in the sequence. And so how does this fit in to the framework? So I think the way that BERT is presented in the Excel net paper is actually a bit more useful. Okay, I don't have it up here, but no problem. So, okay, so you can see how if you consider your G of phi here to be a transformer encoder, and sorry, your G of omega to be your transformer encoder, and your G of phi to be just an embedding lookup function. So in this case, lookup just means the embedding vector that you give to the model before, the embedding vector that you give to the model for each word type. And so you can see how it fits in the framework if we just choose the appropriate G of phi and G of omega. And the way that BERT is trained is it doesn't use negative sampling, but instead the full vocabulary set. And so that's BERT, and that's how it fits in the framework. They do discuss here a key difference between the two models. So the representations that are produced from Skipgram are word type representations. And so if you give it a word, no matter where the word might appear in the context, you will get the same representation. But in BERT, because it takes a whole sentence as input and produces word embeddings from that, the word embeddings are contextual, and it isn't just a simple lookup. So that's the main difference.
Yeah, you can go even further, because if your task involves two sentences, the word representation depends on both sentences.
Right.
So even if you have the same sentence and you change the other sentence, the word representation is going to change every time you change the other sentence. So it's truly task specific.
Definitely, yeah. Okay. Were there any other questions or comments before going to the next part? Okay, so let's talk about XLNet and how it fits into the framework. So I'm not sure if we've discussed this before. I know we haven't discussed the paper, but the main idea, and we'll see how it relates to BERT. I think I'd like to actually just bring up the XLNet paper here. Okay. So the main idea behind the model is, given a sequence, you want to sample a permutation order of the sequence, and then you decompose the joint distribution of the sentence according to that permutation order. So here are a couple of examples of how the joint distribution can be decomposed. And in the case of the permutation order 31524, so here you would have P of x3 and P of x3 and P of x1 given x3 and P of x5 given x1 and 3. And so what the model does is it okay, the point I was trying to make is, in practice, it doesn't actually permute the sentence itself. It uses a mask, an attention mask, so it just applies an attention mask to words which come after the target word in the permutation order. So an example here is, if x4 is the target word, then you would apply an attention mask to the x5 token. And so you're only considering the tokens before in the order. Yeah, so the idea here is that because you are sampling a permutation order at each step, as the model trains, in expectation, you would learn from context on both sides, and so yeah, so the model, like BERT, learns bidirectional context. So another key difference is that it uses a transformer XL instead of the transformer encoder. I don't think this is a difference which pertains to this paper, but another key difference is that it uses, instead of using just one self-attention mechanism to get a representation of a sentence, it actually uses two-stream self-attention. So in essence, what this does is it produces two representations of the same sentence, one of which applies a mask at the target position and one which doesn't. And so in essence, the problem that this solves is you can, if you don't do this, you can get a model which can predict the same for different target positions. And so you can imagine if you have a permutation where the order is the same up to a point, and afterwards it's different, then you might have a target position is different, a target position that you're interested in that's different, but the model would give the same output nonetheless. And so if you're interested in the exact details, then the ExcelNet paper explains it very well. Okay, so how does this relate to BERT, and how does this relate to the framework that we're interested in? So they argue that because the two streams share one set of parameters, that the permutation language model is just a BERT model, or part of a BERT model, the MLM, except you are applying random masks in the encoder to tokens in your sequence. And the masks depend on which permutation order is sampled. So they give an example here. Yeah, they give an example here. So at the kth layer, if you want the representation of the first word, you would only consider the attention score from the third word, and yeah, from the layer previous, and the same idea for the fifth word, and so on. So, okay. Yeah, so this table here provides a nice outlook of well, a nice comparison of these different methods and how they fit into the framework. This essentially describes how yeah, no, okay. I think, okay, I wasn't sure what I was supposed to say here, but that's fine. Were there any other questions that somebody wanted to ask before going on to the actual proposed objective?
I think that it's just if you're a bit confused as to how the GW and the G5 are defined and how they fit the objective, that this table is the place to go, because it says very well it just says what is the so what is the training architecture, so how each of them trains, and then how do you translate it to the current framework. So we usually ask, like, okay, how would this impact my current workflows? So if you're using a transformer-based model like BERT, you would use this table to sort of say, okay, I define my GW as the transformer, and then G5 as the lookup, and so on.
Right. So, okay, they make the point relating to this table. They make the point in this section that the main thing that's driving progress in this framework, the models in this framework, is the G of omega here, so the encoder. So that is the thing that has largely driven the progress. Excuse me. And okay, you can see why that's the case from the table, but of course there are other reasons why, and also they do mention that there are many other pre-training objectives that are not mentioned in this paper, which also fit in the framework. So like Elmo and GPT-2. Okay, so the model discussed in this chapter, it combines part of BERT and a model called Deep Infomax. So this is a method for getting mutual information-based representations from images. And part of its objective is based on maximizing the mutual information between different views of an image. So actually specifically global and local features of an image. So how does this relate to sentences? So in this case, for the global representation of the sentence, you would input the sentence into a transformer encoder, which is what they use, and the hidden state of the first token is given as the representation of the sentence, so the global representation. And so this is because the first word is assumed to be, as it says here, assumed to be the special part of the sentence symbol. And you see something similar in BERT as well, where the a linear transformation and softmax is applied to the hidden state of the first token. Yeah, so that's for the global representation, and for the local representation, it's simply just the embedding lookup of each token. And so defining these two views of a sentence like this, you can then use the contrastive learning framework and maximize the mutual information between them. There's another point here about where masking should happen. So whichever target word you're interested in, the global representation has to be generated by masking the word of interest. Otherwise you get the context based on, you get a representation of the context based on the word that you're actually interested in. Okay, so the way that they make this analogous to Deep Infomax, so which uses patches of an image, is instead of using individual words for the local representation, you use n-grams of a sentence. So in practice, I think I'll skip to this section briefly. In practice, the way that the training examples are generated is by, first of all, sampling the n in n-gram from a Gaussian, which on average will be 5. And then anytime you want to sample an n-gram from a sentence, you would iteratively do this until you reach 15% of the sentence length, which you would then mask. So that's how the training examples are gotten in practice. Another nice thing about this this objective here is that you simply, because your two representations are that of the entire sentence and n-grams of the sentence, you can simply use the same transformer to encode both. And so as you can see in this table, you don't need to use a different lookup. You can just use a transformer for both g omega and g phi here. And yeah, other than that, it's the same. You're just defining these two functions, and okay, so that's deep info max. Now the actual objective that's presented in the paper is one which just combines the masked language model from BERT and the deep info max. But the only difference between the MLM here and BERT is that instead of performing a softmax over the entire vocabulary, you use negative sampling to construct the negative sample set, again by sampling from the unigram distribution. Okay. So we're coming towards, well, close to the end of the time. Were there any questions up to this point? No? Okay, great. All right, so let's go through the experiments section. So there are three models which are compared. So it's the BERT model, the BERT noise contractive estimation, and InfoWord. So we've discussed these three. These two. The BERT NSE is just the re-implementation of BERT that the paper uses. So yeah, as it says here, they remove next sentence prediction. They approximate the softmax, and instead of having the model at training time see two sentences separated by a separating symbol, it just sees one sentence. Yeah. Okay. So we talked about how the training examples are generated for the deep info max. Let's talk about results. So as with testing seeing how good the representations are for many other in many other approaches, you would test it on the set of natural language tasks, blue, and they also test the representations on the Stanford question and answering task. So reading comprehension from Wikipedia articles. So how do the models perform? So it seems like it depends on the task, and it seems like the InfoWord model performs better on specific tasks. So you can see that it performs better than the BERT NSE on question and answering and accepted linguistic acceptability. So this suggests that because instead of using a word as your local representation, use an n-grams of the word, the model is better at understanding longer phrases, and so they suggest that because these tasks require that type of understanding more. There is also the point about BERT outperforming the BERT NSE on a number of glue tasks, and actually outperforms it on average. And they suggest that this is because well, this is because, first of all, intuitively it makes sense because BERT is trained with the next sentence prediction task, but also, yeah, but also because at training time, the model sees 2 sentences, but for the BERT NCE, this only happens at inference time, and the separate symbol is only introduced when it's required in a downstream task. So, okay, these are the results. As far as the discussion section here, I don't think I had anything to say other than I guess we can wrap up the paper by saying that there's, you know, they present these methods and unify them under a framework, and this framework is quite flexible. You have great choice as to which views of a sentence you would use, and so they basically talk about how the future directions of this approach are exciting because you know, they think including more complex views, so like higher order or skip n-grams, could lead to some interesting results in the future. Yeah. So were there any questions before we finish?
I've got a question, might be a little bit off topic. Did they at any time try to quantify the mutual information for each model?
No. So as was mentioned before in the chapter here, the mutual information can't be explicitly formulated. So in terms of theoretically why, if you want to understand, and I think I'd like to dig into this as well, then this is the paper that they reference. But yeah,
thank you. Yeah,
you only maximize the mutual information by maximizing a lower bound on it.
Yeah, thank you. I'll take a read.
Great.
Very good paper. Thank you very much. And well, you've gone through the detail very well for me anyway. So thank you.
Thanks. Okay, so if there weren't any other questions, then thank you.
Yeah, thank you very much, Amin. It's a very interesting proposition in this paper. I like the idea that they took this very original, like the original idea behind word embeddings, which was maximize mutual information so you can get good representations, and they applied it to a very recent technology which basically forgot about it. And they show that it's still a valid principle for representing language. So yeah, it's really cool. So yeah, if there are no more questions, we'd like to thank everyone for joining the discussion. As usual, if there's a particular paper that you want to discuss, or if there's a topic that you have in mind and a few papers in mind, please do send them to us. You can go to nplan.io and you can find all our contact information there. Otherwise, some people have been putting like issue requests in GitHub. Please feel free to do that as well. And finally, we are actively recruiting for roles involving machine learning, data science, software engineering. So if you are interested, please do get in touch with us. All the roles are in nplan.io/careers. And we'd be more than happy to speak to you about a future at nPlan. Thank you very much, Amin, and thank you everyone for joining, and see you next week.
Thank you.